Okay, May, June 2019, paper 6, variant 3. In question 1, some students are determining the mass of a block Q by a balancing method. They are using the apparatus shown in figure 1.1. One student places the meter ruler on the pivot at the 50 centimeter mark and then places block Q with its center at the 5 centimeter mark. So block Q should be centered at what? At 5 centimeters. Suggest why it might be difficult to place block U accurately at the 5 centimeter mark. Why might it be difficult? Well, block U might be larger than the ruler, right? Block U might be larger, slightly larger than the ruler. So if you remember, okay, if you remember the when you had a larger block which was larger than the ruler, how could we find the center exactly? We took the average readings before and after the object, right? So the it's difficult, okay? It's quite difficult, okay, to find the center, the center of the block. How can I find the center of the block? By the average method. Take the average of the readings before and after the block. Before and after the block. That's it. To have reading 1 and reading 2, and then you need to take the average of these readings. Soon places block M on the meter ruler as shown in figure 1.1 and adjusts the position of block M until the meter ruler is as nearly to being balanced as possible. Briefly describe a method to find the position at which Okay, briefly describe a method to find the position at which the meter ruler is as near to being balanced as possible. One very common method of finding whether this ruler is balanced or not is moving it slowly until it balances. That's it. Okay, so move the block slowly. Move the block, okay, slowly back and forth until the ruler balances. Back and forth until the ruler balances. Okay. As for the previous question, if you had a larger block, this is block U. If the larger block, it actually blocks, okay, it covers the readings behind it. So how can I find the center of this block? Just take the reading before and after. For example, if the reading before was 3 and the reading after was 7, okay, so how can I find the average? 3 plus 7 divided by 2, which would be 5 centimeters. Okay, for B, just move the block slowly until it balances. In II, we have a table and we need to plot the graph of B on the y-axis, B on the y-axis, and A on the x-axis, A on the x-axis. You do not need to start the axes from the origin, okay, which is even better. Let's start. A is 45, 40, 35, so we can start with 25 on the x-axis, 25, 30, 35, 40, and 45. If you want to start with 20, it's okay. Okay, all the way up to 50. If you want to start with 20, 25, 30, 35, 45, yes, it's okay. What about B? From 38.6 all the way up to 65.5. I guess it would be logical to start from 35. Let's see. If we start from 35, 40, 45, 50, 55, 60, huh, would it be enough? Would it be enough if we start from 35? Let's count again. 40, 45, 50, 55, and 60. So it's not enough, right? It is not enough. So I think we need to use a different scale of tens, right? You need to use a different scale of tens. We start with 30, 40, 50, 60, 70. This would be an okay scale. And then let's start plotting 25, okay, 25 in the A with 38.6, which is 39, which is 39, okay. Can I use 35, 45, 55, and 65? You can start with 35. Yes, you can do that. Start with 35, 45, 55, 65, 75. Yeah, that would be okay. Now, 25 and we said 38.6, which is 39. Okay, 25 and 39. So this point over here is 39. And 30 with 45. I guess this is easy. 30 and 45. Yeah, this point is 30 and 45. Right. 35 and okay, 35 and 51.8, which is 52. Okay, 52. 40 and 59. 40 and 59 over here. And then last but not least, 45 and 65.5. 45 and 65.5. Okay, right over here, this point. Now the points, can we plot the points or can we draw the graph? Yes, we can draw the graph, straight line. This is quite obviously a straight line. Okay, that's it. A very easy. Can I approximate the points? Yes, you can approximate the points, especially if it's 60. For example, the point was 51.8. So it's very difficult to plot 51.8 in this graph. So you can plot as 52. Yes, you can plot it as 52. Um, okay. Now, moving on to to the next question. He wants to find the gradient. How can I find the gradient? You have to use the triangle method. Okay, using the triangle method. Okay, you have to draw a triangle on your graph. You have to draw it. If you do not draw it, you will lose a mark. Rise over run. Y2 minus y1 over x2 minus x1. Okay, y2 minus y1 over x2 minus x1. Okay, should I extend the line? If you want, you can extend the line. If you'd like, you can extend this blue line. Now, let me remove the line. Definitely, you will not remove the line. You have the blue line. Okay, y2 minus y1, which is 65.5 minus 40 minus 39. 65.5 minus 39 over 45 minus 25. What is this? Slope minus 39 over 45 minus 25. This is 1.325 or just 1.3. Okay, this is 1.3. Okay, can I find the mass using this equation? G minus 1 times K. Can I find this? Yes, can I? G minus 1, okay, 3.125 or 3. It's 1.325. So you can write it down as 1.3 or 1.33. Again, it's the same. Can I use this equation? Yes. So it's 1.33 minus 1 times 200. What is 1.33 minus 1 times 200? This is 66. So the mass, mu, is 66. What is the unit? What is the unit of the mass? What is the unit of the mass? Yes, it should be grams. Huh. Do I have to use the triangle method? Yes, you must draw the triangle. You must, it's a must. Okay. There's no other option. You have to draw the triangle. What about the numbers? What about the numbers you use? If you want, you can use the numbers from the table, or you can use the numbers from the line. Again, this straight line, the numbers would be very close to the numbers from the table. So if you use the numbers from the table or the numbers from the line, it is okay. But you have to draw the triangle. It's a must. Okay. And okay, the mass is 66 grams. The student suggests, okay, yes, you should round to the nearest whole number on the graph. A student suggests that A and B are proportional. State whether the results suggests this. Are they proportional or not? Let's check out the numbers. Okay, let's check. How do I know, or how can I determine whether two numbers are proportional or not? By dividing two numbers. For example, by dividing two numbers. B 65.5 and A is 45. What is 65.5 divided by 45? Using the calculator, 65.5 divided by 45. This is 1.45, right? 1.45. If I take any two other numbers, 51.8 and 35. What is 51.8 and 35? 51.8 divided by 35. This is 1.48. 1.48. So are they proportional? Are they proportional? Yes, they are proportional. Should I say that from the graph there is a straight line that starts from the origin? No, I cannot say that. Why? Because it does not start from the origin, right? But the question was very specific. He asked me, are the values of A and B proportional or not? So 1.45, 1.48, yes, they are very close. If you use any two other numbers, if you use 38.6 and 25, for example, 45 and 30, and you divide these numbers, yes, you would find these numbers to be very close. 1.4 something, 1.5, which are within the limits of experimental accuracy. So the statement, yes, they are proportional. Okay, yes, A and B are proportional. Why? Because the values of B over A, that's what I keep on doing, okay? B over A is, well, let's write down the values of B over A, okay? The values of B over A are close and within, okay, within the limits of experimental accuracy. Can I say that the graph has a positive gradient? No. Oh, it wouldn't help with this question. Not this question. There's another question in which you have actually a graph which is a straight line. I know this is a straight line, yes, but it should start from the origin. It should start from the origin. For this graph, how can I say that the values uh, are proportional? He didn't say directly proportion, did he? He just said proportions. So how can I state that the values are proportional? By dividing two numbers. By dividing this two numbers. Way past the no. I'm talking about B over A and B over A. So what did I do? 65.5 and 45. This is 1 point. This is value. This is a value. And then the other number is 51.8 and 35. This is a number, another value, 1.48. Are these two numbers close or not? Are these two numbers within the values of experimental accuracy or not? Yes. What am I doing? I am dividing B over A. I keep on dividing B over A, the larger number by the smaller number. For example, let's try out 38.6 divided by 25. What's 38.6 divided by 25? This is 1.5. Okay, this is 1.54. What is 1.54? Is it close to 1.48? Yes, it is close to 1.48. Still within the limits of experimental accuracy. Okay? Now, a student is investigating the transfer of thermal energy between hot water in a beaker and cold water in a glass boiling tube. Okay? What are you doing? You are transferring energy from a hot water in a beaker, and then to the cold water inside this test tube. Can I record the room temperature theta R? Yes, I can record the room temperature theta R, which is 21 degrees Celsius. Soon pours cold water into the boiling tube. Okay, he pours some water into this test tube and hot water into the beaker and hot water into the beaker. He places the boiling tube into the beaker of hot water. He takes this tube, okay, and places it into the hot water, right? The whole tube as it is, with the cold water inside it and with the thermometer inside the tube, right? We have You have cold water now inside this tube. You have cold water here. And then you have hot water here. You place the whole tube inside this larger beaker. He records the temperature every 30 seconds. Temperature of the cold water, theta C, and the hot water, theta H. I want you to think about this experiment. Okay, I will not go down now. Okay, I will not scroll down. I just want you to think about this experiment. You have cold water here, right? You have cold water. When you place this tube inside the hot water, what will happen to the temperature of the cold water and what will happen to the temperature of the hot water? If you place cold water inside hot water, the cold water itself will start to increase. The temperature will start to increase. And the temperature of the hot water will start to decrease, right? So the temperature of the hot water will start to decrease, and the temperature of the cold water will start to increase until they reach equilibrium after some time. I just want you to think about what's happening in the experiment. That's all. Now, can I complete the table headings? He said complete the table headings. Can I complete the table headings? Yes. The time is in seconds. The temperature, degrees Celsius, and degrees Celsius. Okay. It is difficult to read both thermometers every 30 seconds. We have thermometer of the cold water and thermometer of the hot water. Describe briefly a technique that would ensure that temperature readings are as accurate as possible. So why would it be difficult? Okay. Or if you want to think about a precaution, taking the readings of these thermometers, can I take the readings of the thermometers perpendicularly, right? Perpendicularly, and make sure that you can see them easily. For example, make sure that you can see the first thermometer and the second thermometer easily and take the readings perpendicularly. That's it. Okay, so make sure. Yes, perpendicularly to avoid the parallax error. Perpendicularly to avoid the parallax error. Make sure you can see both thermometers easily. And take the readings perpendicularly. Take the readings, okay, perpendicularly to avoid what? To avoid the parallax error. Can I complete the table with the temperatures? Yes, I can complete the table with the temperatures. You need to add 30, 60, 90, 120, 150, and 180. Okay. Now, write a conclusion stating how the difference in temperature between the cold water and hot water affects the rate of heating of the water in the boiling tube. So where is the water in the boiling tube? The water in the boiling tube is this temperature, okay? It keeps on increasing, right? It keeps on increasing. Yes. Okay. So initially the temperature or the greater temperature was 69 degrees, right? 69 degrees. And it increased by how much? It increased by almost what? Almost 11.5 degrees Celsius, right? Initially when you had a huge difference between the two numbers, okay? How do we know the numbers in the time column? Because in the question he said he takes the reading every 30 seconds on the previous page. Anyway, so the greater the difference, greater the temperature difference, the greater the rate of heating. The greater the rate. How do you know that? Again, initially, the temperature difference was 69 and it increased by how much? It increased by 11.5, right? By the end, almost by the end, the temperature difference was only 15. right? The temperature difference was only 15, and it only increased by how much? It only increased by 4, right? It only increased by 4. That's it. So the greater the temperature difference, oh, the greater the temperature difference, the greater the rate of heating, you can say. Okay, the rate of heating, but you need to reference the table. How can I reference the table? Okay, for example, initially, at first, the difference was 69 degrees Celsius, and the rate. You don't actually need to calculate the rate. You can just write down the values or the difference between the two temperatures. Difference between the two temperatures, which is 19.5 and 31. The rate was 31 minus 19. 31 minus 19.5, which was equal to 11.5 degrees Celsius. Okay. Okay. By the end. Okay. By the end, the difference was 15 degrees Celsius, and the rate uh, was 63 minus 59, which was equal to 4 degrees Celsius. What is the equation? You don't need the equation, but the equation would, if he actually told you to calculate the equation, okay, the equation would be the difference in the temperatures divided by the time. Divided by the time. For example, the difference in the temperatures in the first question, in the first part was 11.5 divided by the time taken, 30 seconds. The second part would be 63 minus 59 divided by the time taken, which is 30 seconds as well. Okay? No, I don't care about the no. We're not saying 74 minus 59. I'm talking about the difference or the rate of heating of the hot water, of the cold water. The rate of heating of the hot water. Again, the cold water. I don't know why I'm saying hot water. Okay, the rate of this temperature. Of this temperature. Anyway, moving on. State what you can expect the temperature of the boiling water or the boiling tube to be when theta c stops rising. When theta c stops, it stops rising. So as you can see, theta c keeps on increasing. Theta h keeps on decreasing. What would the final temperature of theta c be? Hmm? What would the final, yes, when the difference reaches zero, yes, I know, when the difference reaches zero, but what could you expect the final temperature of theta c be to be? No, not this number, not no. What could the final temperature of them be? It could be, yes, it could be 68. Someone could say 68, someone could say 66, 67, 69, right? How am I predicting these numbers? Think about these differences. Okay, so think about these differences. Let me use another color. For example, it increased by 11.5, and then it increased by what, 8.5, right? Keeps on increasing, and then here it increases by 5, right? And then it increases by 4, 5, and then 4. Then someone could say it would increase by 3, and then 2, and then 1, right? It will increase by 3, and then 2, and then 1, which is, you'll add 6. If you add 6, it will reach 69. Someone says, no, I will add only 5, reaching only 68. Again, it's okay, right? Why? Because temperature increase, the rate of increasing this temperature keeps on decreasing. I don't want you to get lost with the words, okay? But as you increase the temperature each time, is it constant? No, it's not constant. In the first 30 seconds you added 11.5, and then in the second 30 seconds you added 8.5, right? And then you added what? This is only 8, right? And then you added what is this? 4 and 2.5, so this is 6.5, right? And 5, 4. Then when you keep on adding 3, 2, 1, so you can add 6. You can add 6. So for example, I'd say in my in my point of view, it would be 69 degrees Celsius. Someone else might say 68 degrees Celsius. It's okay. Okay, it is okay. Why? Because the okay, rate of heating decreases, decreases. Okay, that will increase by only 6 degrees. It will increase by only 5 degrees, by 7 degrees maximum, maybe. So some of you might say, why wouldn't it be the room temperature? Why wouldn't it be the room temperature? This is because it's only after a couple of seconds. We're talking only maybe after a whole minute or 2 minutes. Okay, this is only after 2 minutes. It has not yet reached the room temperature. When will it reach the room temperature? In II. When you leave the beaker after a few hours, after you leave the beaker for a few hours, it would reach the room temperature, which is 21 degrees Celsius. If you leave the beaker for several hours, it would reach the room temperature. So this is when you can say, yes, it would reach 21 degrees Celsius. But for this statement, the cold water keeps on increasing in DI. The cold water keeps on increasing the temperature. It will keep on increasing until it reaches almost 69, maybe 68. Someone might say it's up to 70. Again, it's okay. Okay. Non-constantly, can I say that the decrease uh, yes, yes, you can say that. You can say that. Okay. Okay. Now, suggest two changes that would be made to the apparatus. Okay. That would be made to the apparatus or procedure to ensure that the temperature theta C of the cold water rises more quickly. How can I make the temperature rise more quickly? How can I make the temperature rise more quickly? By decreasing the initial temperature of the cold water. Decreasing the initial temperature of the cold water. And someone might say, what if I use a metal tube? Yeah. What if I use a metal tube? Would this help? Yes, it would help. Why? Because a metal is a good conductor of heat, right? So it would rise more quickly. It's a good conductor of heat, so it would rise more quickly. Yes. Moving on to question 3. Okay. Can I say increase the temperature of hot water? Yes, you can say that. You can say increase the temperature of the hot water. Okay. Okay. Yeah. Figure 3.1, draw the symbol for a voltmeter across resistor X. Okay. Across resistor X voltmeter. Hmm. Read and record. Okay. Read and record these readings. Can I read these readings? Yes. The current would be 0.22. And the current would be 0.22 and the voltage would be 1.1. Voltage would be 1.1. Can I complete the table headings? Yes, the current in amperes, the voltage in volts, the resistance in ohms. Okay. Soon suggests that the current should remain constant when the voltmeter is used. State whether the readings support this suggestion. Are the current readings, are they constant or not? 0.22, 0.23, and 0.24. Or 0.21, I'm sorry. Are they constant? Yes, they are constant. Yes, they are constant. Okay. They, hmm, why? Why are they constant? Huh? Why are they constant? Because the numbers or the values are very close within the limits of experimental accuracy. So the values are close and within hmm, the limits of experimental accuracy. If you want, you can measure or you can calculate the experimental accuracy. You can say 0.23 divided by 0.22 or 0.22 divided by 0.21, whatever you like. You'd find them to be very close. Can I find the resistance of each of these resistors or each of these combinations? Yes, I can find the resistance of each of these combinations. 1.1 divided by 2.2. 1.1 divided by 2.2. This is 5.0, right? 5.0. 3.3 divided by 0.23, which is 14 ohms. And then 5 divided by 0.21, which is 20, very close to 24 ohms, right? Very close. I'm writing only two significant figures. Why? Because the whole table is two significant figures. So I'll write down the values as only two significant figures. Hmm. For resistors in series, the total resistance of the combination is the sum of the individual resistors, right? Use your results from table 3.1 to calculate the resistance of Ry and Rz from the table. X on its own was 5 ohms, right? X by its own was only 5 ohms. Can I find Y? Can I find Y from this table? Is Y 14? Can someone say that Y is 14? No, Y is not 14, right? Y is 14 minus 5. Why is it 14 minus 5? Because this is the combination of X and Y plus Y. So if Y or if X is 5, then Y would be 14 minus 5. 14 minus 5, which is 9. Okay, 9 ohms. What about Z? Can I find Z? Can I find Z? Yes, it would be, you have X and Y and Z. So 24 minus 14. 24 minus 14, which is 10 ohms, right? Which is 10 ohms. Yeah. Circuit components are to be rearranged so that resistors X, Y, and Z are in parallel. The ammeter measures the current. The voltmeter measures the potential difference across the resistors. So we need to rearrange them. Okay, instead of them being in series, we need them to be in parallel. You have the power supply, you have the switch. Okay, let's draw them. The power supply and the switch. And then you have an ammeter. And then resistor X, resistor Y, and Z, and the voltmeter in parallel to them all. Okay, so this is X, Y, and Z. That was easy. Soon sets up the circuit as described in EI. She measures the current IP in the circuit and the potential difference VP. She uses these values to calculate the resistance RP of the resistors in parallel. RP was 2.3. Okay, she found the total resistance of uh, these three resistors in parallel. Use the student's result and your result from table 3.1 to compare RP with the resistance of RS of them in series. So RP was 2.3. Is RP equal to RS? RS, which is the resistors of the resistors in series. The resistors of them in series was what? Of the three resistors in series was what? Was X, Y, and Z was 24. It was 24. Is RP equal to RS? Definitely not. 2.3. Is RP equal to 10 times RS? Is RP equals equal to 10 times RS? No, it's actually the other way around. It's actually the other way around. How so? 10 times RP. What's 10 times RP? 10 times RP, which is 10 times 2.31. 23.1. Is this equal to 24? Are they both equal? Yes, they are both equal. Yes, they are both equal within the limits of experimental accuracy. They are both equal within the limits of experimental accuracy. That's it. Okay. Okay. Hmm. A student wants to investigate the factors that affect the height to which a ball bounces when it is dropped. You have a ball, drop the ball. Huh. Plan an experiment that will enable him to investigate in detail how the height from which a ball is dropped affects how high it bounces. Okay, how high it bounces. How can I solve this question? Okay, how can I prepare this experiment? How high? Okay, how high? Okay, how the height? We need to find out if the height affects how high it bounces. We'll keep on changing what the only factor that we can change is the height from which the ball is dropped. That's all you need to do. This is the range of values, right? The range of values. So first of all, if you write down the range of values, okay, the range of values, the height, okay, of the ball when it's dropped, and then we need to state some values for this height. Some logical values might be, let's say, 20 centimeters, 40 centimeters, 60 centimeters, and 80 and 100 centimeters. So you have five values, right? Five values for this drop. Any additional apparatuses? Well, one very important apparatus would be the meter ruler. Definitely, you need a meter ruler. You definitely need a meter ruler. This is the missing apparatus. What about the controlled variables? What about the controlled variables? If you think about it, you have a ball which is being dropped. You have several controlled variables. First of all, the mass of the ball, right? Can I write down measuring tape? Yes, you can write down measuring tape instead of meter ruler. Same surface, which it bounces off from. Yes, okay. You have okay, same type of surface. These are the controlled variables. Controlled variables. Same surface of the floor. Same mass of the ball. Can I say same size of the ball? Yes, you can say the same size of the ball. Same material. Okay. Same material. Sheets of different floor coverings. Well, that's you just need to make sure that they are the same sheets, the same, for example, number of sheets. That's the same floor covering. Okay. Will the volume affect the experiment? Yes, if you use a different ball, it might affect the experiment. Same surface area of the ball. Okay, but it's the same volume basically, or the same mass, or the same ball. Basically, you are using the same ball. What about the apparatuses? Definitely, you need to write down the meter ruler or the okay apparatus, meter ruler, or if you want to say the measuring tape, it's okay. Hmm. What about the steps? So we wrote down the additional apparatuses, okay, and we wrote down the state, the key variables. Can I write down the precautions? Yeah, we can write down the precautions. One very important precaution would be take the reading perpendicularly to avoid the parallax error, right? So one very important precaution, this question, take the reading of the height perpendicularly to avoid parallax error. To avoid what? The parallax error. Okay. These are this is one of the most important precautions for this question. What about the steps? How can I conduct this experiment? Okay, release the ball. You have to release. Do not throw the ball. Okay, release. Let me write it down in brackets. Don't throw the ball. Okay, from a height and measure the height of the bounce, the height of the bounce from the floor. You can say repeat for different heights dropped. Repeat for, okay, different heights dropped. Hmm. Okay, and can I draw a table? Yes, he wants me to draw a table. Okay, explain briefly, precaution. Can I draw the table and then write down a conclusion? If you want to draw the table in this empty space, it's okay. If you want to write down the table on the dotted lines, again, it is also okay. So you have the table, okay, the height of the drop, which is in centimeters, okay, and the bounce height, which is also in centimeters. Okay, not bad, right? Last but not least, I need to include the conclusion for each value of the height, okay, for each value of the height dropped, for each value of the height dropped, you have to repeat the experiment, okay? Repeat the experiment and take average, record the readings, in the graph, in the table, I'm sorry, in the table. If you want, you can compare the readings. Okay, compare the readings by plotting a graph. By plotting what? A graph of the height versus the bounce. Okay, the height from which it was released versus the bounce to which it bounces back again. Okay. Okay.